Okay. Hello. Can you hear me?
Yes, sir.
Oh, okay. My name is Ibrahim. How do I address you? Are you Adeboye?
Adeboye, sir. Adeboye, sir.
Oh, okay, okay. So we can start now. So the meeting is being recorded. So for those who are not here, they'll probably just get the recording afterwards. So let me share my screen. Okay, let me know if you can see my screen.
Okay, I can see it now.
Oh, okay, all right. Okay, so welcome to this bootcamp. And in this particular session, we are going to be talking about embedded systems design. This is the first session, so it's going to be more of preliminary introduction and some background knowledge and just some background information and needs. So before we get started, let me just ask you what's your level of embedded systems knowledge? Are you a beginner or have you been doing some design already? Yeah, just give a quick summary of where you are.
Okay. My level, I'm not really new to embedded system entirely because I've been doing some designs already.
Oh, okay. Well, what kind of design have you done before?
Yeah, I've done like a project using Arduino
Okay.
system.
All right. Just Arduino, you've not used like PIC or maybe STM32 or something different.
I've not used them. Though I was taught PIC at the time, but I didn't really do any project with it and carry on with that.
Oh, okay. So maybe then maybe I can still call you a beginner then. Kind of,
Okay.
kind
It's
of.
okay, sir.
Yeah, because if you've done just Arduino and you've done projects with just Arduino, then I mean, it's still kind of like basic level thing because almost anybody can do anything with Arduino. That's the fact. So maybe yeah, let's just leave it like that. So my name is Ibrahim, and I'm a PhD student at the University of Minnesota. I had got my BSc from AU in 2018, and I studied electronic and electrical engineering in my undergraduate. Although now I'm doing mechanical engineering for my PhD. Interesting. So I'm interested in electronics, hardware, and I'm also a robotics enthusiast. So I like robots a lot. And I also do some kind of graphics design. Yes, I do some graphics design on this side. It's kind of like my hobby. And I'm sure you noticed that in these slides, I took my time to make sure that these slides look very nice and you don't get bored by my slides. So in case you want to reach out to me, you can reach out to me on LinkedIn. My name is Ibrahim Oladipo, so you can just check that on LinkedIn. I prefer to get connected to on LinkedIn than any other thing. Yeah. Okay. Oh, okay. So seems someone is trying to join the meeting. Oh, okay. All right, I got that. Someone was trying to join the meeting. Sorry. So for this session, we are just going to talk about, we're going to do an introduction, talk about the foundation, and then we're also going to talk about some basic electronics theory, and then we also discuss some basic electronic components, and then we just end there. I don't want this session to be too long, and it's not really a practical section anyways, so it shouldn't be super long, and you start getting bored at some point. Yeah. So let's get started. So if you have any question at any point, you can just bump in or you can just signify. I don't think there's a way to signify. Even if you signify, I may not be able to see it. So you can just cut me in and let me know that you have a question. Yeah, is that cool?
Yes, sir.
Okay, all right. I also want this session to be as interactive as possible. So I might also be asking questions. So be ready for questions and then try to provide answers as much as possible because it's going to be very nice if it's more interactive than me just talking for 1 hour or how long. All right. So who is this class for? So this class is more for beginners. Even if you've used Arduino before, I believe you also gain a lot from, this whole bootcamp. And yeah, and even if you've used more than Arduino, maybe you've done some PIC programming, but you're still doing some very basic projects. I believe this is going to be relevant and useful to you. But for people that are already like experts, they are started designing 4-layer PCBs, you're doing 2-layer PCBs and more complex stuff. I think this class is going to be very boring for you. I mean, my own session especially, because I try to go as basic as possible. Yeah, so and then we are all learning, and learning never ends. So, or we are probably on different levels. Maybe that's where the whole intermediate, beginner, and professional comes in. So I think it's more about the experience as well. It's not just about what you've learned in terms of theories. It's more about what you've done. I mean, maybe you've the kind of projects you've done. Even Arduino, you can go very complicated with Arduino and do some really complex firmware projects and things like that. But it all depends on what you've done with those things, anyways. Yeah. So I think that's what separates maybe beginners from intermediates and from professionals. Yeah. So that's like what this class is all about and who this class is for. Yeah. So I want to start with this question that people usually ask. I mean, is Arduino enough? When you know Arduino, can you really call yourself an embedded systems engineer? Maybe not really, because anybody can use Arduino. I've seen posts online where people talk about people from maybe a lawyer picked up Arduino one day and was able to do a project with Arduino in one single day. So you can't really say Arduino is, I mean, if you know Arduino, you can really say you're an embedded systems engineer if it's just Arduino. And Arduino is not just the hardware, right? Arduino is like a complete ecosystem. So you have the software, the Arduino software, you have the Arduino hardware, you have the Arduino community. So Arduino is like a big, massive community, and it's like a big, massive ecosystem. So when you talk about Arduino, I mean, if the Arduino hardware and the Arduino software is the only thing that well, you can't really call yourself an embedded systems expert anyways. And Arduino is for hobbyist students and professionals. When I mean professionals, even people in the industry, some people use Arduino for things. Uh, like for example, maybe you have a project in mind and you and test. I mean, something that you can use to test ideas, yeah. And it doesn't really require so much time and so much effort to get things to work, yeah. So that's like part of the reason why Arduino is very important. But if you want to go to more advanced levels, like more advanced firmware development and yeah, some really complicated industrial design or anything, yeah. So the Arduino platform hides so much details from you that it's almost like it's owed to your hand and you don't really get into the tiny bits of details. So you may not really be able to do so much complicated stuff with the Arduino platform. So that's where you need to start, looking at other more sophisticated things like maybe STM32 and the ARM microcontrollers, ARM-based microcontrollers and things like that. Yeah. And also if you need more power than what the Arduino can provide, Arduino is just like, I think the Arduino speed can probably go up to 20 megahertz. But now we have microcontrollers like the Tin-C that do up to like 600 megahertz, very fast. I mean, if you need more power, and those things are like 32-bit MCUs. So if you need more power and yeah, more power and more sophistication, then you need to start thinking beyond Arduino. Yeah. All right. Does anyone have any question at this point? I think I should just be asking that. Maybe you have a question about if you should stay in this class or not. Yeah, you can just ask. Oh, Eric just joined. Eric, are you with us? Can you hear me?
I can hear you.
Oh, okay. Yeah. Do you have a question?
No, sir.
Oh, okay. But what do you have to say about, I mean, everything I've said so far? I've not said much, but just say something anyways.
He said, okay, like just knowing Arduino and doesn't really make you a professional. Just like the basics, just like the basics, what anyone can do. Even someone that doesn't have an idea like that can also use Arduino.
Yeah, someone that doesn't have an engineering background can also use Arduino. Yeah. Oh yeah, I think you got the idea. Yeah, that's basically what this whole slide is all about. So just open your mind and be open to interesting other more complex level hardware design and embedded system design stuff. Yeah. Okay, let's move on. Okay. All right. So let's start by defining what embedded systems what embedded system is. So embedded system is basically a combination of hardware and software. That is, you have the hardware part of it, and then you have the software part of it. And embedded systems are usually designed for a specific purpose. So what that means is, for example, the motherboard of your computer, right, is an embedded system. So it's designed for a particular purpose, right? It's designed to serve the purpose of being a motherboard of a computer, and that's just what it's designed for. The the embedded systems in your maybe your phone, for instance, is also designed for a particular purpose. And you can also look at things like maybe these things for weighing, all these weighing scale, this weighing electronic weighing scale. When you stand on it, it tells you what your weight is and things like that, or what your mass is. Yeah, sorry, it tells you what your mass is. So those things, the electronics inside those things are designed just for that particular purpose. Yeah. So that's like what embedded systems are. So embedded systems are a combination of hardware and software designed for a specific purpose. And usually embedded systems are usually embedded in a larger system, like maybe a larger mechanical or electrical system. So you notice that a lot. For example, the motherboard of your computer is embedded inside the whole computer, whereby inside the whole computer you have a couple of other things, and then the motherboard is just part of those other things. Inside our computer as well, you have your power supply, which is also like another embedded systems of its own. So you have a couple of embedded systems coupled together to form the larger system. So some examples of hardware, you have like inputs and outputs peripherals, then you have the processor, you have the memory, and a lot more. So those are like some of the hardwares that you can maybe think about. And yeah, can you just mention a couple of embedded systems that you just look around you right now where you are? I'm sure there are a couple of embedded systems around you. So just give some examples of some of the systems you have around you, or that you think they are embedded systems. Yeah. Oh, are you there?
I'm still here. I'm just trying to look around. Okay. Let's say
Oh, okay.
no, the AC I have here, I can't say maybe it's embedded system. Maybe let's say those ones are smart ACs that auto that can detect temperature.
Oh,
Then
yeah,
I
definitely. Yeah, there's definitely embedded systems. Yeah, you have embedded circuits, or you have embedded circuits boards inside those things. If you tear it up, I'm sure you find some PCBs somewhere inside that. Yeah, that's embedded system stuff as well. So it can detect temperatures, right?
yes, sir.
And then it can adjust itself to
Temperature.
compensate for the excess or for the change in temperature, which is really interesting. Yeah, nice. That's a very good example. Yeah.
Yes, sir.
Um, so now let me talk about this. I found this on GitHub somewhere, and I believe it's going to also be relevant in setting a direction for this session. I mean, not just the direction, and also giving a general idea of what embedded systems design is all about. Oh, do you have a background in electronics and electrical engineering or mechanical engineering or something close?
Mm, I'm a student of electrical electronics, yeah, engineering.
Oh, okay. Yeah, that's cool. All right. So that means you've probably done things around soldering before, and then maybe you've done some circuits courses like this foundation of electric circuits or fundamentals of electric circuits and all those theories. You probably
Yes,
have
sir.
idea of those things already, and maybe you've also done courses on analog and digital electronics. So like those are some of the basic things that I mean they are very important for every embedded systems person. Yeah, you need like you must know some of those things. For example, you must know how to solder, you must know about analog and digital electronics, and you must know some binary arithmetic, like converting from hexadecimal to binary and some of those other things. So those are like very basic fundamentals that are very important. You must know how to read schematics and how to understand the interconnection of components and figure out okay what this is what this part of the circuit is doing and things like that. So, and you must also know about EST. EST is like electrostatic discharge. So have you heard about EST before?
I can hear you, sir.
I said, have you heard about EST? EST, like electrostatic discharge.
Uh, okay, I've heard about it inside a book when reading a book
Oh, okay.
about
So
trouble.
what do you understand by EST?
Uh, can let me say example now when we are working on a PCB, some circuits like a capacitor now.
Yes.
Is it a couple that they have some charges even when they are disconnected from the power? They
Oh,
will still
okay.
have some charges in them. I think that is what I
Yeah.
can.
Yeah, that's still related to this. So I think another part of this is, even you yourself, your body can get charged up sometimes.
Yes, sir.
And especially during the winter, maybe like during the dry season, sometimes when you comb your hair you notice this kind of sparks coming from your hair, or maybe when you put the comb close to something you notice that some things are reacting to the comb after combing your hair. So those are some of the electrostatic, like there are some electrostatic buildups that happens to our body sometimes. And when you touch if you touch an electronic, maybe a printed circuit board with so much charge in your body, you can damage the printed circuit board, because when you touch the printed circuit board, it's almost like you are like transferring so much charge from your body to the printed circuit board. So you can damage the printed circuit board through that. So you need to understand those things to make sure that when you are designing systems or when you are working on projects, you don't mess things up without knowing, because you can actually damage things without knowing that this is the reason. You just realize that, oh, this thing is not working, and you start wondering why it's not working. But those are some of the reasons why things may not work. Yeah. So those are like very basic level things, like all those things I just mentioned. So you need to have this as like, yeah, like a must. Yeah. And then after knowing those things, then you can start talking about things like multimeter, oscilloscope, function generators, and logic analyzer. So these things are also very important, especially when you want to start talking about debugging. I mean, these things are very important. We may not really be able to go through details, but I'm sure there are resources online that you can, get linked up to and see how some of these things are being used. But the most important thing is for you to actually use them yourself. Yeah. So if you don't use it and you watch videos, you may think that you know how to use it, but not until you try to use it. I don't think you really know how to use it. Yeah, from my recent experience designing printed circuit boards. So I find these devices very important, like logic analyzers, oscilloscope, multimeters. I don't really get to use function generators, but it's also important to know all of these things and how they operate. The only other issue with this is like they are quite expensive, so it's maybe difficult for you to own one personally, or except maybe for multimeters. Yeah, multimeters are not too expensive to have, but for oscilloscopes and logic analyzers and maybe function generators, yeah, they can be expensive, but you can also build function generators. I've seen some basic projects online using Arduino or using things like STM32 to build. to build function generators. So maybe the oscilloscopes are like the most expensive ones on this list. Yeah, but you should try as much as possible to have these tools if you really want to be an embedded systems engineer. Yeah, they are very important tools. Okay, and so then, so still on the entry level, right? So then, you start talking about microcontrollers, and when you use microcontrollers, what you talk about is like or some of the components of microcontrollers that we commonly use are like the ADCs. ADCs are the analog to digital converters. And we also have DACs, like digital to analog converters, PWM, pulse width modulation, and some other things, timeout, watchdog. Do you know about like why do we need ADCs and DACs?
The reason why we need them because there are some, let's say we have analog signal and digital signals. So
Okay,
let's say we are interacting with our environment. Most of the signals we have in our environment are analog.
cool,
So we need to, and for microcontrollers, because majorly they work with digital signals.
cool.
So
Yeah,
we need to convert those analog signals to digital signals.
yeah, that's nice.
And also, digital to analog converter is like the inverse of that, converting from digital to analog
Analog.
signal back.
Yeah, that's nice. That's nice. Cool. Do you know about PWM as well? Like PWM, this. Have you used
And
PWM before?
I just add about pulse width modulation. I
Yes,
think it's part of
that's
an
PWM.
analog signal. I don't know. It's part of analog signal when something is modulating
Okay.
at an interval. I think so.
Okay. Can we really call it analog? Maybe not.
I'm not sure.
It's like I think it's like a blend of analog and digital in a way.
Okay,
I don't think
but
we
it's not
can really call it
really
analog,
digital.
but so it's like you have like 0 volts, you have 0 volts, and then you have like 5 volts, right?
Yes, sir.
So you are trying to PWM allows you to go between 0 volts and 5 volts, but the variation is
Okay,
happening digitally. I don't know if you
okay,
get it. So
I
it's
get
not like
it.
you are using analog voltage directly, but you have like pulse. You are modulating pulses of. So like for example, let's say you have the PWM signal that looks like this. I mean, each period looks like this.
Okay.
So this is like let's say if this is 50%
Huh? I can't hear you. The network.
50%.
Okay, I can hear
So
you
you have
now.
50% of 5 volts, right? So which is like
Okay,
2.5 volts. So it's almost like
fine.
you have changing this digitally, but you're also getting variation in some analog way.
Okay,
And then another thing about the PWM signal is it's like moving at the signal is changing at a very high frequency. So maybe sometimes like maybe I can't remember the exact frequencies, but maybe like 250 kilohertz or something. So it's changing so fast. Yeah, it's changing very fast. So that's why you can't get stuff like this. I don't know if that makes sense, but you can also change this to maybe 25%. When you change this to 25%, then you get 25% of the full voltage. So that's kind of like what you get with PWM signals. No, I'm not sure we can call this analog or digital, but to me, it's almost like a blend of both worlds. Yeah. And then, have you heard about timers as well? Timers and watchdog.
Mm, timers. I just only what I know about timer is just 555 timers. When I see that, I see. It's only what
Oh,
I
okay.
can see.
So microcontrollers also have like timers. Microcontrollers usually have timers. Some microcontrollers have multiple timers built inside them. So what you can do with timer is like you can, for example, let's say you have a particular application where you want to use a microcontroller to do something after some time interval, right? So maybe you want to say every 5 minutes or after counting 5 minutes, yeah, the microcontroller should do something. So the timers inbuilt in those microcontrollers allow you to do stuff like that. So you can configure those timers and you can have different settings And yeah, it's really cool that you have those features in those microcontrollers. So you can have a recurring maybe event, and then you can use timers to control such an event. I think something is known on this list, interrupts. There's something else called interrupts. Do you know what interrupts are as well?
I'm trying to recall because I've used it in a code having to interrupt. Okay, I can't actually recall what it's about now.
So
Is
interrupt
this
is like
also go on,
oh,
sir?
okay, did you? Oh, okay. So you know the microcontroller is like the microcontroller runs in a loop, right? So you have like a while loop. Maybe you have like a long set of code instructions, and then you keep running the same set of code, right? You have a loop, right? So the
Okay, sir.
interrupts is like let's say you want to like you want something to, like when something happens, you want your microcontroller to stop whatever it's doing and respond to that thing that is happening. For
Okay.
example, on your computer, what happens when you move your mouse? What happens when you move your mouse cursor? Like when you move your mouse, what happens to the mouse cursor? The mouse cursor always moves, right?
Yes, sir.
That may not be the best example of an interrupt. So let me use a different example. Okay. Okay. I designed something recently. It's like a bicycle indicator, like a bicycle trafficator. So it has like two LEDs, two sets of LEDs. Some LEDs are pointing in the left direction and some LEDs are pointing in the right direction. So the way I designed the system was the microcontroller had a loop, like a continuous loop. But whenever I pressed the any of the buttons, it responded immediately to that particular button I pressed. So even if it was doing something else at that point, it would still respond to my button press. So that's like interrupt. We are interrupting the flow of the loop basically. So interrupts give you some kind of power, right? Because there are some events that that are of high priority, and you don't want to miss those kind of events. Does that make sense? You don't want to miss those kind of events, so you want to make sure that whenever you want that particular event to, or whenever that particular event happens, you want to make sure that you get that information at that point, and you want to do a particular action at that point as well.
Okay, sir.
Yeah. So I'm trying to remember another example, but just imagine that you have a car, right? Let's use the case of a car, and you are trying to use the trafficator, but the car is playing music, or the car is doing something else, and you are trying to
Okay.
press the trafficator, you are trying to turn left, and the car does not respond to you. What could happen in that kind of situation? Right? I mean, it could cause an accident. So
Then
some events or some actions are of high priority, and you want to make sure that whenever you need to perform those actions, you have that highest priority to perform those actions. So although there are other ways of also doing this, there's something called I think maybe real-time operating systems. So there are other ways of doing that. Yeah, maybe not through interrupts. Yeah, if there are ways of assigning priorities, but when you go into more details of embedded systems, I'm sure you find those stuffs. Yeah. Yeah, so that's what interrupts are. So timers, watchdog is kind of like another kind of timer. I can't remember what the definition of watchdog is, but or I can't really figure out a way to explain what watchdog is. So watchdog is like a way for you to monitor your system if your system is still operating the way it's supposed to operate. So it's almost like a how do I say this? It's almost like a check mechanism. So, for example, you have like a watchdog that runs every 5 minutes to check if your system is operating the way it's supposed to operate. So, the way the watchdogs are designed, the ones I know, there are multiple types of watchdogs, right? So, some are designed in such a way that maybe every five minutes you send a particular message to your microcontroller, and your microcontroller sends you a response, right? So, depending on what you get as a response, you can tell whether the microcontroller is working the way it's supposed to work or not. So based on that, you can maybe turn off the system and to avoid some maybe some crazy things. I mean to prevent some crazy things from happening. So do you understand?
yes, sir.
Yeah. So maybe another way to say that is maybe you have someone has like kids, and then every five minutes he asks the kids to come report to him. and then maybe at some point a kid came to come and report to him, and the kid was maybe saying nonsense or saying something out of context. So maybe you can start thinking, oh, maybe this child is not okay or something like that. So that's kind of like what watchdog is. Yeah. So those are some of the peripherals I usually have in microcontrollers, and then we also have protocols like
So wait, what
I2C.
about DMA?
What do you say?
DMA.
Oh, I can't remember what DMA is right now. That's why I skipped it.
Okay.
Yeah, I can't remember what DMA is. It's an acronym, but I just can't remember what's the full meaning of DMA is. Yeah, if I remember later, I'll probably come back to it.
All right.
Okay. So then we have protocols like serial communication protocols. So these protocols allow you to communicate with devices, maybe like some other external devices, or it also allows microcontrollers to communicate with microcontrollers. So protocols are like, maybe, for example, we have different languages, right? We have Yoruba language, we have English language. So when I'm speaking, if I speak Yoruba language to somebody that does not understand Yoruba language, what's going to happen?
Don't respond.
Exactly. The person wouldn't even understand what I'm saying. So I need to first make sure that, okay, this person understands Yoruba language, right? And then I speak Yoruba language to the person, and then we can communicate. So protocol is like a well-defined standard for microcontrollers or for devices to communicate, right? So it's almost like languages for, not really languages, but you get the idea, right? So just like ways for things for machines to communicate with each other, or for devices to communicate with each other. So we have like SPI, we have UART, we have I2C. So each one of these protocols has its own advantage or advantages and disadvantages. For example, I2C, you can connect multiple devices with using just two wires. That's one very interesting advantage of I2C. You can connect multiple devices, like maybe I can't remember the limit, but you can connect a lot of devices using just two wires. Yeah. So that's like one very interesting advantage of this. Yeah. And then maybe an advantage of SPI, maybe the speed. I think SPI can go much faster than I2C. So maybe that's another advantage of SPI. Then USART, can't remember the exact advantage of USART. But these are just like protocols that used to communicate between microcontrollers and between, you know, things like maybe you have like some other ICs. So there's this project I'm working on. So there's this amplifier. So it's like an amplifier IC. It's like a standalone amplifier IC. It has like 32 channels. Yeah. So when you power this, the only way to talk to this amplifier IC, for instance, is to use SPI. Yeah. So the amplifier is connected to maybe some external inputs, right? And then the only way to get data from this amplifier or to configure this amplifier is to use SPI communication. So yeah, so that's just an example of how you use SPI to communicate with devices. And then you have some advanced protocol. You have like SATA. I can't remember the full meaning of this. PCIe, USB. We all know USB. USB is universal serial bus, MOST. Yeah, just like it says, they are advanced. Even me, I myself have not really used all of this. I think maybe just USB, yeah, once in a while. Yeah, but maybe when you get to advanced levels, you probably touch things like this. So those are some basic things that you need to know when some of the things you need to know when you program microcontrollers, or when you program, yeah, microcontrollers anyways. Yeah. And then also we talk about languages. Yeah. So there are multiple languages used to program in embedded systems. Some people use C, some people use C++, some people use Python, assembly. I can't really say which is best, but C is like, from what I know, C is the closest to hardware level. Oh no, C is not the closest. Assembly is the closest to hardware level, and then maybe C is the closest to assembly, or maybe C and C++. Anyways, as long as it does what it needs to do, I believe I mean, you are good to go. But usually, from my experience, they usually recommend that you learn maybe C or C++, and then you also learn assembly. Python is not so popular. Python is just becoming very popular now that you have things like MicroPython, Circuit Python. Have you heard about MicroPython and Circuit Python?
No, sir.
Oh, okay. Those are some of the really new, interesting ways of programming, microcontrollers. Yeah, it's really, really nice. Yeah. So now we have like microcontrollers that support direct programming with Circuit Python and MicroPython. Yeah, it's really nice. You should probably check that out after this after this talk. Yeah. So you can use
Yes, sir.
Python to program chips as well, to program microcontrollers. Yeah, it's really nice. Python is just everywhere. You can use Python for almost everything and anything. You can use Python for web design. You can use Python for data science. You can use Python for this, that. It's almost like Python. Python is a language that almost everybody should learn because it's very versatile. And when you know it, it's almost like you have a huge asset. I mean, it's very important to have that kind of asset. So that's talking about code, right? Then we also have like design patterns. We have object-oriented programming, control structures, single thing. I don't know what this is. Yeah, but you probably know about object-oriented programming already. Do you know what
I didn't
object?
I didn't know about that. Though I'm doing a course on Python. Though currently where I am on Python now is the object oriented programming.
Oh,
I
okay.
don't know how it's applicable to embedded system now.
Mm, okay. Oh, interesting. Oh, I'm sure you will get to, when you use things like libraries, some of those external libraries are designed to use OOP kind of. For example, when you use some sensors and you use some libraries of those sensors, maybe when you finish going through the object-oriented programming, you understand better. So, you can create instances of, sensors.
Okay, sir.
Just like when you have in OOP, you can have like instances of a particular class, right? You have a class,
Yeah,
and then
class,
you can
yeah.
create instances of that class. For example, you have maybe class human, and then you can create an instance, maybe Adeboye of class human. You can create class instance Ibrahim of class human. So maybe you can have a generic, for instance, in a embedded system, you can have a generic library for some particular sensor, and then
Yes.
you can now have like multiple instances of that particular sensor library. Does that make
Oh,
sense?
makes sense. Huh?
Yeah, maybe you can say sensor one of class something, and then sensor two of that same class, and then you can say sensor one dot something, that kind of thing. You have stuff like that in embedded systems as well. That's like on the very basic level. Maybe on the advanced level, you might have more complicated stuff than that. Anyways.
Right, sir.
And then there's also something called real-time operating system. This is also something a little bit more advanced. I'm also just learning more on this. But maybe when you get to that level, or if you're already on that level, maybe you can say something about it. Don't let me assume you're not on that level. But real-time operating system is like more advanced way of programming things like microcontrollers. And I was talking about interrupts earlier and talking about priority. I mean, those are some things that are very uh yeah, they are very important when it comes to real-time operating system. Yeah, I wouldn't be saying much about that anyways. And then also on the software side of things, you also need to know about version control. Do you know about Git already?
And
Or do you use GitHub?
I don't use it, but I usually it's common within developers where they
Yeah, yeah. Yeah, it's important to use tools like that because it helps you. Git is really powerful in the sense that, you can, if you keep track of your code and of the changes in your code using Git, and then maybe you've made like 500 changes, you can always go back to a particular point. For example, if you make 500 changes and then you make 501 change, and then something goes wrong, and something stops working right, you can easily go back to the 500th change, or you can even go back to 480 change. You understand? So those are some of the things, that some of the advantages you get with Git. And also Git allows it's helps with collaboration a lot. You can have multiple people working on the same project, and yeah, it makes it easy for them to collaborate without causing so much obstruction and problems. Those tools are very, very important. Okay. In this same regard, you talk about memory. Memory is also something that is important to know. So you talk about SRAM, DRAM, NAND. No, SRAM is like static RAM, and then DRAM is like dynamic RAM. So each one of these also has like advantages and disadvantages. I will recommend some books at the end that have some things about this. I don't think we should really go deep into this right now. And then you have methodologies. I don't know what this is. TRLV. Oh, okay. This is like methodologies for developing maybe solutions. Yeah. V-cycle, TRL, Scrum. I think I know V-cycle a little bit. I've read these things in the past, but I never really used these things. So that's that's why I can't really remember this. Yeah, so those are like the entry level stuff that you should probably know, or everyone needs to learn and have an idea of these things. So it's actually good to also do something, do a project, or do projects that use these things. Just like I mentioned earlier, if you learn these things without using them, you really don't know it. Yeah. So you really need to use it and be able to prove that, okay, yes, I've done this with this, I understand how this works and things like that. Yeah. So industry specific, then you have some more advanced level stuff. You have the automotive industry, you have aeronautic industry, you have consumer electronics industry and things like that. So when you go at when you go to that advanced level, you need to start thinking about some of these things and some of these standards and some of the protocols associated with maybe each industry or any industry you're interested in. And then yeah, so I have domain specific knowledge, artificial intelligence, filter design, digital control. So there are some specific like RF design as well. So there are some other specific things you need to know for each one of those things, for each one of these other fields. So in case you want to, maybe specialize in one of those fields. Yeah. So that's the end of that. Do you have any question? So that's just like the end of the introduction. I believe that was a good introduction. Assuming that was a good introduction, although it was a little bit long, but I think it's also important to, talk about that. Yeah, what do you think?
Okay, you can move on, sir.
Oh, okay. All right. You don't have any question?
Not down, sir.
Oh, okay. All right. So then another thing that is also very important, like we talked about earlier, is like the basic electronics, the background electronic knowledge, and all the theories that are essential. Maybe not all of the theories, but the very important theories, and also getting to understand why each electronic component is important. Yeah. So I have I have a couple of slides about electric charge and modeling electric circuit, but these are extremely basic, and these slides are for people that are not from electrical background. So since you are from electrical background and you are the only one here, so whoever is not here that is not from electrical background can probably go through this and maybe read this. So the only thing I'll probably talk about is the relationship between voltage, current, and resistance. Do you understand the relationship? Like, how can you explain the relationship between those three?
Sir, I can't hear you.
Oh, I said, how can you explain the relationship between, how do you understand the relationship between voltage, resistance, and current? I mean, what I mean is, what's your own way of explaining this?
If I should explain it, I'll use, let's say, the flow of water. I'll use the analogy.
Okay,
The
all right,
current is like the water flowing through it.
all right,
Why the pipe, let's say the pipe or the stop, that is the resistance. So
okay,
as the size of the pipe is, that's how the water will flow. Then the pressure
mhm.
of that water is the
Yeah,
voltage.
yeah, that makes sense. Yeah, that makes sense. I actually have that in the next slide. So you have like a water tank, and then you have water in the tank. So the pressure of the water is like the voltage, right? And then the flow of the water is like the current. And then the constriction, maybe you have like stops at some point on along the pipe. So those are like the resistance. So this is very basic, but I believe this is like a very important thing to know, because everywhere, almost everywhere all your electronics design, you talk about voltage, resistance, and current in one way or the other. Yeah, so these are very important basics that everyone needs to know. Okay. Okay, so this slide talks about, the importance of resistance and why resistance is important. I was asked this question once, like, why do you need resistance at all? Do you even need resistance? If you have voltage and you have current, why is that not enough? Why do you need resistance? So resistance is important because we want to be able to limit the amount of flow, right? For example, if that the tanks we have in our houses, if the water in the tanks just flowed without you being able to tell that, oh, okay, I want small water, I want tiny bit of water, I want this much water. It wouldn't make sense, right? Because every single time you open your tap, you are opening to the full capacity, which doesn't make sense. So the resistance allows you to vary how much water you have in the case of the tank, and in the case of circuits or embedded systems, it allows us to vary the amount of currents that flows in our circuits. Yeah. So that's like basically why resistance is needed. So then Ohm's law is the theory that relates resistance to voltage to currents, and these are very basic things, and this is for people that don't really have electronic or electronic background. Uh, okay, this is also some basic theories. Maybe something to also mention is that we have like circuit elements are classified based on energy generation into active elements and passive elements. So active elements can generate energy. So examples are batteries and op-amps, operational amplifiers, and passive elements cannot generate energy, resistors, capacitors, and inductors. So that's just by the way. Okay, let me skip all of this. Oh, okay, this concept is very important, but it also requires some sort of calculation. So, but as you can see at the bottom, I already referenced a textbook. The textbook is written by Alexander Sadiku and Sadiku. Yeah, it's Fundamentals of Electric Circuits. This book has details on some of these things, and it's really important to learn these things, because when you go further, you don't want to start worrying about fundamental stuff. You want to know this once and for all, and just forget about the fundamentals. It's not like you're going to forget the fundamentals. You're going to be using the fundamentals, but you don't want to have problems with fundamentals when you go very deep into embedded systems. So it's good to have this knowledge, and to have this knowledge in your tools bag or skills bag. So one other thing that I've noticed is when we draw circuit diagrams in class, we usually draw them like they are straight, of which in real life circuits are not straight. So I realized at some point that people used to have problems analyzing circuits, thinking that circuits are straight wires. Yeah, but sometimes, many times I find out that when you actually redraw things in curved form, not just the straight form, it can be easier to analyze stuff that way. Yeah, that's one thing I've noticed, and while doing my teaching experience or previous teaching experiences, I've tried to do that, and it's used to work for people. When you try to redraw circuits in maybe the curved form instead of just the straight form, it helps people to understand those circuits concepts better. All right, so this is continuation of those things. Oh, okay, I'm going backwards. Okay, these two laws are also important laws that you need to be able to analyze circuit diagrams and schematics and things like that. So this states that the currents going at a node and leaving a node, the sum of currents at a node is zero basically, and then the Kirchhoff's voltage law states that the sum of voltages around the closed path is zero. Yeah, that's like voltage around the loop is zero. Yeah, so that's like what this law says. But it requires, these laws require that you do maybe some practice on your own and you really understand how this really matters in real life. Okay, this is more about Kirchhoff's law. Yeah, that's all about the fundamental theories I have. So now let's go into some more interesting stuff. Just give me a second. Let me get something. Oh, are you there?
I'm still here.
Oh yeah, just give me a second now to get something.
All right.
All right. Okay, I'm back. Uh, let's continue. So let's talk about some basic electronic components, like electronic components that you find on almost, or that you find in almost every circuit design out there. So let's start with resistors. Or maybe I should ask you first. Oh, okay, let's just start with resistors. So resistors are, I mean, components that are used to limit. They are usually just used to limit the amount of current that flows, just like we explained earlier when we were talking about resistance. So they help to protect excessive current flow. Yeah. So you can use different resistor values depending on the kind of limitation you want to impose on the current flow. Yeah. So resistors are also used for voltage division. Voltage division is that, let's say you have 5 volts and you need 2.5 volts as a place, you can use resistors to divide that voltage into two. Yeah, that kind of thing. And then, yeah, you use resistors for voltage divisions. So another thing that resistors are used for in design is pull up and pull down. Have you heard about pull up and pull down before?
No, sir.
Oh, okay. Pull up and pull down is like oh, okay, let me explain this way. For example, let's say you have an integrated circuit that looks like an IC that looks like this. Oops. So you have an IC with pins that looks like this. So you have, this is a pin of an IC, right? So if you don't connect anything to this pin, the pin is floating, and this floating pin can, let's say it's an input pin, right? You set it as an input pin. So
Okay.
this pin is floating and you don't have anything connected. So as this pin is floating, you can have, I mean, it can pick up stray charges from outside.
Okay.
Yeah. So, but what you can do is, instead of leaving it to float, you can maybe pull it down. When you pull it down, when we say pull down, you are pulling it down to ground. So you can just connect this to ground this way with a resistor. So this is 0 volts. So this is a pull down. This is a resistor. So that this also, if this is 0 volts, then it puts this voltage at this point at 0 volt as well, right? But another thing that this allows you to do is you can change the voltage. Are you following?
Yes, sir.
So this resistor allows you to have the assurance that the voltage at this point is the voltage you want it to be. Yeah. So it's not just floating. The the point is not just floating. This point is not just floating. That's one of the things that we use pull down and pull ups for. So another reason why we use pull down and pull up is yeah, I think I just explained that. You want to change from a particular voltage to another voltage. So these resistors they give you the room to do that. Yeah. Yes, that's what that is kind of all about. And then you also use resistors for limiting the capacitor charge rate. You know, if you want to charge capacitors, you have to connect. You don't have to, but I mean, usually we connect resistors in series. Why is this thing misbehaving? Resistors in series with capacitors like this. So if you want this thing to charge very fast, you can use maybe a okay, the charging constant is RC, right? So maybe you can use a bigger resistor. And if you want it to charge smaller, you can use a smaller resistor and things like that. So you can, resistors are used to limit capacitor charge rate. So another place where this is useful, like where capacitor charging and discharging is useful, is maybe you are designing a very high frequency something, and you, or maybe you are designing a high frequency LED blinking circuit, yeah, and you need to control this, and then maybe you want to use analog control or something, so you can use the charging of capacitor and discharging of capacitor to maybe control stuff like this. Yeah, maybe not the best thing, but in theory this also works. And then another thing about resistors, we have like variable resistors. Variable resistors are resistors that you can vary the resistance. So why do you think you would need a variable resistor? Are you there? Can you hear me? Hello? Oh, okay. I think I'm the only one here. Uh, okay. Anyways, variable resistors are, I mean, resistors that you can vary the resistance. For example, let's say you have like the volume knobs of your maybe your speakers at home or your televisions or some things like that. Maybe all those old televisions, they should have volume knobs. So what some of those things have behind the scene is like you have a variable resistor. So as you are varying the resistance of the volume knob, you are increasing or reducing the voltage. Yeah, that could be an application. So another application of variable resistors is maybe you have like a temperature set point for a temperature controlled system. So if you vary the resistance of the, maybe you have a temperature controller that looks, or the control part that looks like this, and then you have a gauge that looks like, maybe you have 10, you have 20, you have 30, and then you have 40. One thing that could be behind the scene is that as you are turning the knob, you're actually changing the resistance of a resistor. So which is an interesting way to, you know, to do that. So the resistor is more or less like an input, and then as you turn this knob, although you wouldn't probably see the resistor, but behind the scene, what you are turning is a resistor. Yeah. So another interesting application of variable resistors is if you look at those game pads. I don't know if you've taken apart game pads before. Can you guys hear me? Oh, okay. All right. So if you've taken apart a game pad before, you know this analog stick on a game pad. So what is behind the scene of the analog stick of a game pad is just a variable resistor. So let me show you in case, I think I have some resistors here. Uh, just in case you don't know what I'm talking about, you can't really know what I'm talking about. Oh, okay. So if you look at this, if you look at this, you can see this has like two variable resistors. It has one on this side and it has another one on this side. So that's one is for maybe the x-axis, and then the other one is for the y-axis. So as you push this down and push this up, you're actually varying the resistance of a variable resistor, basically. So that's an example of an application of a variable resistor. Yeah. And then resistors also come in different packages. The picture on the right shows one of the resistor packages that we have. I mean, this is a DIP package. Yeah. So these ones are the ones that you usually use on your breadboard, and yeah, and you also use it on printed circuit boards as well. Let's go on. And then another thing to also remember is you have resistors are made from different materials, and different materials have different advantages. So when you are designing maybe some very sensitive electronics, so there are some you need to consider the type of resistor material you are using. For example, when you're designing military based or military application electronics, so those electronics usually require some types of resistors. I mean, they require some types of resistors because you want to have the highest reliability and highest kind of quality for those things. So those applications require some specific type of resistors. So I'm also going to recommend a book at the end. I have a copy of the book here. So the name of the book is PCB Design and Layout Fundamentals for AMC. This book explains some really important, I mean, some, yeah, it explains the types of resistors and the application use case for each type of resistor and where you probably need to use a particular type of resistor. Yeah, so that's important to know. Yeah. Capacitors are also like very important components that you find on almost every circuit. Just like I said earlier, capacitors store energy like a battery, and they are used for things like blocking DC currents or for smoothing power supply voltage. Yeah. So you want to you remove spikes on your power supply. You want to keep everything stable and you want to avoid things getting damaged. So you use capacitors for doing things like that. So capacitors are also used for timing, like I mentioned earlier. Maybe you want to time the blinking and unblinking of an LED or something. So you use capacitors. And if you remember the 555 timer, I think Adeboye mentioned the 555 timer earlier. You can remember that to configure the 555 timer, you need capacitors and resistors, right? Can you remember? I don't have this circuit diagram of a 555 timer here, but you are basically discharging and charging a capacitor. That's like what you are doing in a 555 timer, or what you probably do in a timer as well. Yeah, so capacitors help you do, or they give you the room to do things like that. So you also have variable capacitors. I've used a variable capacitor before when I was designing. There was this project I was working on sometime. I was designing a wireless charger or wireless charging system for a mobile phone. So the variable capacitors allowed us then to vary the impedance of your how do they describe this? I can't remember the exact way of describing this, but the variable capacitance just basically allows you to vary capacitance. And when you vary capacitance, you can vary impedance because capacitance is the impedance of a capacitor is inversely proportional to the capacitance of the capacitor. You have something like J J omega C, right? If I'm right. So if you increase the capacitance of a capacitor, then you reduce the total impedance. And then if you reduce the capacitance of this capacitor, you increase the total impedance. So those are some of the things that the capacitors, I mean, variable capacitors give you. And yeah, this find application in some really interesting fields. And there's some really cool stuff you can do with variable capacitors as well. Also, there are different types of capacitor packages and different types of capacitors that have different advantages over each other depending on what application you are focusing on. So we have Mylar capacitor, we have capacitors, and what I've learned is some capacitors are very good at high frequencies. Some capacitors are not very good at high frequencies. So if you are doing designing something that along the maybe gigahertz range or megahertz range, there's some specific type of capacitors you want to use and things like that. So just like I mentioned earlier, this book explains a lot of that stuff. Also inductors. Inductors store energy in magnetic field, and yeah, they also block AC currents, and they also use like as filters sometimes. I mean, there's a specific type of inductor called ferrite bead, and this is used for suppressing high frequency noise on power supply lines. I'll show you some circuits that use this, and yeah, it's also used for protecting voltage spikes. Yeah, so that's like the basics of all of these components, and these are components that you use for almost every design you do. You use capacitors, you use resistors, you use inductors, but inductors are not usually common, but it's good to know about them in case you have an application and you need to use an inductor. Yeah, are you following, or are you guys there?
Yes, sir, we are following.
Oh, okay. Do you have any question at this point before I move on?
Okay, the circuit you showed us now, is it for what is the purpose? And is that you want to show us the circuit that uses inductor? Is it this?
Oh, now I'm going to show you circuits that I use. I'm just going to try to explain like the use of each of those components that you mentioned earlier. So this circuit has you can see capacitors, you can see inductors, right?
Okay, sir.
Yeah. So just like we mentioned earlier. So what happened is this the signal on this wire on this cable, or how do we say it? The signal coming out of this serializer, this point here. Uh, can you see what I'm drawing? Let me try and
Yes, sir.
change. Okay, so the signal coming out of this point is it's kind of like a serial signal. So a serial signal is like changing at a high frequency serial signal. You have a signal that's probably this is just an example, anyways. Does not necessarily have to be like this. So the signal is changing, right? Are you following?
Yes, sir.
So the signal is constantly changing between maybe let's say 5 volts. Let's say 5 volts, and let's say this is 5 volts, right? And then this is 0 volts. So the signal is constantly changing between 5 volts and 0 volts at a very high frequency. Yeah. So what this whole thing here allows you to do is this part allows you to do is yeah, you want to use this same signal to power a device. Does that make sense? You know, when you want to power a device normally with DC voltage, you need a voltage that is like this. That is just 5 volts, right? You need a voltage that is at 5 volts constantly, right? When you want to power maybe Arduino or something, or you want to power an IC. Are you following?
Yes, sir.
You need a DC
Yes, sir.
voltage. So what you are trying to do with this circuit is you are trying to generate a DC voltage out of an AC kind of voltage. This is almost like an AC. It's alternating, right? So you're trying to generate DC from this AC. So the signal that is coming from here, from this serializer, or that is on this line is AC. Yeah, you can see coax, right? The signal here is AC. So what you need at this serializer place is AC. This entrance, this point, you need AC. But you also want to power this device. This device needs DC to be powered. So you are tapping the AC signal from here, and the AC signal is going through an inductor. What does an inductor do?
Blocks AC current.
What did you say?
Blocks AC current.
Exactly. So you are using this inductor to block the AC part of the current. So what you get at this point is no more AC, right? It's kind of like DC in a way, but it may not be super stable, but it's kind of like DC. So that's what you are using this inductor here to do. So you are using it to block the AC, and then you are getting DC at this point. But you also use this capacitor. You remember we talked about capacitor earlier, that we use capacitor uh to smoothing out a voltage. Oh, what did I do? For smoothing, right? So
Yes, sir.
you use this capacitor to smoothen whatever signal you get from here. So because the signal that the inductor is giving you may not be super smooth, but this capacitor also helps you to keep things smooth, right? And then you also you now put whatever voltage you have here goes through a regulator, a voltage regulator. And then maybe you have 5 volts here, and then you want 1.8 volts at the end here. So the voltage regulator helps you to do that, right? And then it gives you a level another voltage. But you still also need to smoothen this voltage. We always use capacitors to keep things stable. So this helps you to make sure that things are stable. So another reason why you need to have this capacitor is, this is a device that is consuming current, right? And the current consumption may not be constant. So the current consumption may depend on what the device is doing at any instant, or at any instantaneous moment in time. So for example, if the image sensor is getting images, so the current consumption may go up, right? Maybe it will go up like this. And then if the image sensor is not taking images, maybe the current consumption will go down, and then maybe it's going up and going down. So that can affect the voltage level at this point. So, but when you have like these capacitors, the capacitors can help you keep things stable. So you get, so that's like one of the reasons or one of the applications of using capacitors. Does that make sense?
Yes, sir.
Yeah. So you, that's like, this is a very good example of a use case of capacitors and inductors. Yeah, I will still show other ones, but does anyone have a question before we move on?
I have a question, sir.
Oh, okay, go ahead.
Capacitor, we said, can be used to block DC current,
Yes.
but
Yes.
in case of where we use it in a power supply circuit where it's used to smoothing out the voltage or current, they said it removes ripples. Normally
Yes.
DC voltage is not meant to have ripples, but a capacitor is used to remove the ripples there.
Yeah.
How is it to remove the ripples when it's blocking DC current?
Oh, the current is not going through the capacitor.
Okay, sir.
Is how do I describe it? If you look at, let me clean up all of these things. Is there a way to quickly clean this up? Erase all ink on this slide. Okay. If you look at this inductor part, right? You can see that current is going through the inductor, right?
Okay.
But in the case of the capacitor, current is not going through. So what's happening is that capacitor is trying to keep the voltage at this point the same.
Okay.
Let me try and explain in another way. Let's say you have a circuit that looks like this. Oops. Uh, oops. Sorry. So let's say you have a circuit that looks like this. This is a battery. Let's say this is a battery, right? Battery, let's say 5 volts battery. And then this is you have a resistor here, and you have a capacitor at this end. So this is a capacitor, and then this is a resistor. So what happens when let's say you have a switch somewhere here. So what happens when you close the switch? What happens when you close the switch? When you close the switch, let's assume the capacitor was initially at 0 volts, right? So let me draw the voltage on the capacitor. So this is voltage capacitor, and then this is 0. So before you close the switch, the capacitor is at 0 volts. Let me use another color so you can see what I'm trying to explain here. So let's say the capacitor is at 0 volts, right?
Okay.
So when you close the switch, what happens? The capacitor charges, right? Depending
Yes.
on the charging rate depends on the RC, the value of the R, right, and the capacitance of the capacitor. So it charges to exponential charging. It charges to this voltage at this point. Yeah, the voltage at this point. So it charges to 5 volts in this instance. So what happens when it charges to 5 volts? After it gets to 5 volts, what happens?
To still be 5 volts.
Exactly. So the voltage is not changing.
Okay.
So the voltage at this point remains at 5 volts. Even when you have some slight change in this voltage, let's say this voltage goes to 6 volts. If this voltage goes to 6 volts, I mean, the capacitor still has 5 volts, but it still tries to like keep things stable and that kind of thing. So that's why they say it blocks DC. DC current doesn't go through this capacitor.
Okay, sir.
Yeah. But the voltage here remains constant, kind of constant.
Okay, sir.
Yeah, that's. I hope that that answers your question anyway. Does that
Yes,
answer
sir.
the question? Okay, cool. All right, let's go to the next circuit. So this is I don't know if you've heard about TNC. TNC is another like microcontroller family, just like the Arduino. But this is another interesting family, and these are like very, very powerful microcontrollers. For example, this TNC can do up to 72. The speed it can go as fast as 72 megahertz. TNC 3.5 can go as fast as I think it can go faster than 72 megahertz, maybe up to 160. I'm not sure. But TNC, for example, TNC 4.0 can go up to like 600 megahertz. Yeah, I'm sure of that. Yeah, I'm presently using one in my lab, and it's really powerful and it's very, very fast. And it also has a lot of interesting peripherals on this whole device. So this is like an open source device. If you go to their website, you find this circuit. That was where I got this circuit diagram from. So if you go to this website, you find a lot of information about things. I believe you should check it out, and if possible, you should try to get one of these guys and play with it. It's a very, very fast and powerful device. Yeah. So if you look at the device, you can see some things. If you look at this page, you can see a ferrite. This is a. Can you remember what ferrite bits are used for? I mentioned that earlier. Are you there?
Yes, sir.
So ferrite bits are like inductors, right? They are used to filter out like high frequency noise. So that's like what they use. Well, ferrite bits are usually used for. Yeah, they are used like filters. You want to filter out high frequency noise, and they are also used for protecting parts of your circuit from things like EMI, electromagnetic interference, and some external noise, and maybe some noise from anywhere. Yeah, so you can see a lot of ferrites on this circuit. Can you see ferrite, another ferrite there? You can see another ferrite here. Yeah, so that's what you use ferrites for. Yeah. So I'm just trying to show you the circuits where they used some of those components. So you can see here, you can see a capacitor here, probably used for maybe smoothing or something. You can see another one here. Yeah, and then you can also see another capacitor here. This is almost like, I believe this should be a voltage regulator from what I'm seeing. Yeah, this should be a voltage regulator. This device here should be a voltage regulator. So yeah, and then you can also see a couple of capacitors here. These are also used for filtering, yeah, for smoothing stuff to make sure things are what things are supposed to be. And you can also see another capacitor here. Yeah, so you can see some resistors here. I'm not sure exactly what these resistors are doing. Oh, okay, I think this resistor. Oh, I can't remember what these resistors do. I've forgotten, but for the USB interfaces, they usually have these 33 ohm resistors. Some other designs use a different value of resistor, but I noticed that USB interfaces use these resistors. I can't remember the exact reason, but you know, that's just another example of resistors and capacitors in action. So it's very important to understand how these things work, because when you are working at this level, you are not supposed to be thinking about, am I supposed to use a resistor? Am I supposed to use a capacitor? You're supposed to know that, okay, this is, okay, I want to have smooth voltage here. So what should I use? So you already have, those that knowledge in your skill set or in your tools bag. So you just basically pick it out and say, oh yeah, this is what I need to use. You don't want to start, doing research and going to Google that, how do I do this? How do I do this? So those are like very fundamental and very basic knowledge that you need to have. Yeah. Any question before we go to the next circuit? I have 3 circuits. This is second one. I still have one more that we can look at. Maybe you have any question about the things here as well that I might be able to answer. No question. Okay, let's move on then. So this is the third one. This one is the circuit for FEDA S2. FEDA S2 is also another interesting and powerful device. You should also check this out. Just go to fedas2.io and you find this circuit at FEDA's website. But this is really tiny. Okay, let me try and zoom in a little bit. Hey, yeah. So you can see this long, what's happening? Oh, okay, it won't allow me to do anything now because I zoomed in. Anyways, but you can see these capacitors here, right? Oh, nobody is answering. Can you guys hear me?
Yes, sir.
Oh, okay. You can see these capacitors here. They are used for the same purpose that we've been talking about. Aha, okay. Do you know what Schottky diodes are? I'm sure you know what diodes are, but maybe you've not heard about Schottky diodes or you've not used Schottky diodes before. So Schottky diodes are like low voltage drop diodes. They still do what normal diodes do, but they have like lower voltage drop. I think a typical diode takes out about 0.7 volts, which reduces the voltage you have at the end. But Schottky diodes like take out lower voltages and you have, I mean, the amount of voltage drop that you get with Schottky diodes is lower and it still performs the same purpose. So Schottky diodes are also like nice components to know about. I've used them before and they're really cool. So that's like one thing about diodes. And then what do you generally use diodes for? Can someone answer that question? I believe you guys have done some designs before. What have you used diodes before in any of your designs? Anybody?
Diode are device that allow flow of current in one direction, and you can
Okay.
use it for rectifying, for convert maybe from AC to DC. You can also use it for regulating in case of Zener diode.
Oh, but when you use a Zener diode, now the question, you define diode as a device that allows current to flow in one direction. But when you use Zener diode, you are using it in the opposite way, right?
Sir?
So does that definition still hold?
Like, well, okay, I would say it's old because you can, if you want to really, you can't use it to, it can't allow flow of current in both directions at the same time. It's either
Okay.
bias or reverse bias.
Yeah,
But
that makes sense. Now that's a better definition. I just wanted to point out so you don't go and define it somewhere and then they start looking at you that, oh, okay. But that's a really nice definition. I think Zener diodes look something like this. The voltage current profile for Zener diodes. Sorry, I'm trying to draw with my pad, but it's really messed up. If I'm correct, they have profiles that look like this. Yeah. Sorry, this diagram is not the best in the world, but I think it should serve the purpose. Okay, so you have something like this. Oops. So you have current here. You have current here, I believe. You have voltage here, I believe. So you have the current only starts flowing at a particular voltage, and then if you forward bias it, and the current only starts flowing at a particular voltage if you reverse bias it. So that's why you can have, so current doesn't flow within this range. So that's why you can have a Zener diode, doing multiple directional, bidirectional usage, kind of. But usually they use it for the reverse bias mode because it helps to keep the voltage constant and things like that. They use it for no, that's not rectification, right? They use it for voltage regulation. Yeah, I think that's voltage regulation. I think you mentioned that as well, Adeboye. Yeah, so that's like what Zener diodes are. So those are very important fundamentals that you need to know. And when you know these fundamentals, they will really help you on the long run or in the long run. And when you are designing more complex systems like this, you wouldn't be worrying about, those very basic and those very basic things. Yeah. So also you can see, we talked about SPI communication protocol earlier, right? So if you look at this, you can start to see those things come into play. You can see SPI here. You can see, I think this is I2C or something. I'm not sure what that is. Yeah, so if you look here too, you can see SPI here. So this is SPI communication protocol. And then I don't know if there's I2C somewhere here. Is there I2C? Can't really zoom in. Let's see. I'm not sure this device has I2C feature, but anyways. Yeah, you can see SPI here, anyways. So maybe this particular device does not have I2C feature. Let me go back one step and come here. Okay. So one of the things that you look at when you are deciding on picking a microcontroller platform for whatever project you want to do is some of these things I'm mentioning. For example, if you need to communicate with a particular sensor and the sensor uses a particular protocol to communicate, you need to make sure that the microcontroller family you are picking can use that protocol. For example, now if the sensor uses SPI, you need to make sure that your microcontroller has the ability to use SPI. Does that make sense? Or let's say your sensor uses SPI at a frequency of 24 megahertz, and that's like the only thing that your sensor uses. You need to make sure that your microcontroller can communicate on SPI at 24 megahertz. So those are some of the things that you need to know. Uh, so the other thing I didn't mention that I think I should have mentioned is data sheets. Do you guys know how to read data sheets? I mean, it's a very important skill that you need to have. Data sheets, reading data sheets is very powerful. So I can show you an example of a case where I messed up because because I didn't read the data sheets very well. So let me show you an example before we conclude. Just give me a moment and let me pull up a file. Hope you guys can still hear me anyways. Uh, project. Oh, okay. Can you see my screen? I believe you can still see my screen and you can see what I'm displaying. I'm assuming you can see my screen. So there's this particular project I'm working on right now, and this is data sheet for the IC I'm working with. So this particular IC uses SPI for communication. If you see here, you can see SPI command words. So the only way to communicate with this IC, the IC is an amplifier, as you can see here, is this an electrophysiology interface chip. So it's like basically an amplifier. So you can see it's a fully integrated electrophysiology amplifier array with on 16-bit ADC. And we also talked about ADC earlier. So you can see everything is starting to come into play. You need to know about ADC to use this. You need to know about SPI to use this IC as well. So you can start to see that, I mean, these things are very important. I mean, these protocols and these all fundamentals are very important to know. So when I was working with this, I kind of messed up a little bit because I didn't read the data sheet very well. So let me show you where I messed up. So this is where I messed up. So when I was reading this data sheet, I didn't see this part, the data sheet. So when I was working with the device, I didn't realize I needed to configure the device to operate I mean, I needed to do a particular thing to make it operate the way I wanted to operate. So I was trying to use this thing with an Arduino, right? And Arduino uses a particular type of SPI, which is like a standard CMOS SPI. Yeah. So there are like different types of SPI again. I didn't talk about that, so I wish I talked about that. So we have different types of SPI. We have like LVDS SPI, and then we have like standard CMOS SPI. I think there are other types of SPI as well. So Arduino uses standard CMOS SPI. So I was trying to use this device with the Arduino, but I didn't realize that the device was already configured by default to work with LVDS SPI. So LVDS means low voltage differential signaling. Did you get that? Low voltage differential signaling. That's what LVDS means. Uh, so I was struggling. I spent several days. I think I even spent several weeks trying to, communicate with the device. And then some weeks later, I read the data sheet and I was like, and I saw this, and then I realized I had wasted so much time because I didn't read the data sheet very well. So I'm just trying to show you the importance of reading the data sheet. So the only thing I needed to do was to connect a particular pin to ground, because when you connect the pin to VDD, then which is like 5 volts, then the device operates in LVDS mode, which was not what I wanted to do, but it was connected to VDD, and I mean, I just wasted several weeks trying to figure it out, or not even trying to figure it out. I wasted several weeks because I didn't read the data sheets very well. So it's very, very important for you to read your data sheets and understand how to read data sheets. Yeah. So that's very important. Yeah. So I just wanted to point that out. Anyways, so does anyone have any question? I think we spent so much time already. It's over 1.5 hours. Any question from anybody? Maybe on one of these circuits or something? No question. Okay. If you have questions, don't be shy to ask questions. Okay. So now let me talk about some book recommendations. Some books I would recommend. First book I recommend is this PCB Design and Layout Fundamentals. I mean, for people that want to design PCBs, you want to design PCBs, you want to learn how to design PCBs. This book is very important. Yeah, it's a very, very fantastic book, and it goes into details. I mean, as regards using capacitors, resistors, inductors, and all other components, and some of the rules you should follow when you are designing PCBs to make sure that things work the way you want things to work. But before you get to that level, if you are still on a very basic level, you should probably start with this Encyclopedia of Electronic Components. So this book explains what each of these electronic components do in details. Yeah, you have like very nice figures in the book that are used to explain what each of those components does. We talked about resistors, capacitors, inductors earlier, but there's no way we can go into, I mean, we can go in depth and really understand how those things work in this short period of time. So if you want to understand these things better, you should really get this book. I wouldn't ask you to download the PDF, but yeah, if you can buy the hardware, that's better. Because you probably wouldn't get the Lego PDF version of this, because maybe the company sells this, so you probably wouldn't have the legal version of this online. So whatever you download online is probably not legal. So if you want to keep things as legal as possible, you should purchase one of this. Yeah, although the books can be very expensive. Yeah, I understand. But anyways, it is what it is. Another very important book to have or to read is this book, Fundamentals of Electric Circuits by Alexander Sadiku. I think they use this book in OAU, Obafemi Awolowo University, to teach electronics. So I have my own copy of this book as well. It's a very nice book. So you should also try to get your own copy if you can afford it. If you can't afford it, I wouldn't say you should download the PDF, but you can find your way anyways. Okay, another very good book is Make Electronics. This also has like it's very similar to this one, Encyclopedia of Electronic Components, but it takes a different approach. It's more project based. I think this one is more project based than this one here. So if you want to go through a project based approach to understand, what resistors are, how to use resistor switches, this has a lot of projects in the book. So you can see here, you can see here they have this learn by discovery icon here. Oops, what did I do? Sorry. So you can see learn by discovery here. Yeah. So it's a very, very fantastic book. I really recommend. I highly recommend the book as well. But maybe you want to start with this. I recommend that you start with this and then maybe you jump to this afterwards. Yeah. and then you also with this as well. Questions? So we reached the end of the session, and I think we have just like 10 minutes, or how many minutes left? 13 minutes or something. So another book I have is this book, but this book is more or less like an advanced level book. If you want to go from beginner to intermediate to advanced, yeah, then this is where to go. I mean, if you want to go from Arduino to more sophisticated level designs, yeah, this is a book to probably read. But anyways, I'll probably mention this later, maybe in our next session. I believe that will be relevant to every one of us. Yeah. So for the people that came late, I just want you guys to introduce yourself and maybe talk about some of the projects you've done before and maybe your background knowledge in electronic and your background knowledge in embedded systems. Do you have an electronic background or do you have a mechanical background? Just say a bit about that so we can understand, or I can tailor my sessions in the best of manners. So I don't just teach what I don't need to teach. Anyways. Yanulua, Ainde, Ridwan, Abdul Malik. Are you guys there? Oh, no one is responding.
Yes.
Oh, yeah, all right. Can you just, say a little bit about yourself? I mean, talk about your embedded systems design experience and expertise. Are you an expert already? Have you started designing? Yeah, go ahead.
I'm new to embedded system.
Oh, I didn't get that.
I said I'm new to embedded system. Yeah, I mean like that. It's just new to the embedded system.
Oh, okay. I didn't really hear that very well. I think your background is a little bit noisy. Maybe you can just send a message on the general group chat on the Discord channel. I think that would be a way to really understand everyone's skills level better. Yeah, maybe I should just probably send a message afterwards too. I think that would be better. All right. If there is no question, then I think we can call it a day at this point. I'll share the link to the recording, or maybe the organizer is going to share the link to the recording. Is the organizer here as well? Can you? Okay, maybe we just discuss that on the group chat anyway. All right, so thank you for coming to this session. If you have any questions, you can drop it on the Discord channel, and if you have maybe any recommendation as well, you can also drop that on the Discord channel. I believe we can end on this note. Thank you for attending this session. I hope you have learned one or two things, and I hope I didn't confuse you as much as I convinced you. All right, so all right, bye bye. Take care of yourself.
Yes, sir.
All right, thank you.